right, so in this one, we're going to be talking about exponentials and then the parts and their equations. So how does it work with compound continuous, compound equations, and then population growth and decay. So we're going to be talking about investing money, losing money, and then population growth and decays. So we are going to be talking about two types of investments. We're going to be talking about compound continuous and just regular compound interest and how they kind of work together, what their graphs look like. So first off, taking a trip back to IM1, so our general just compound interest. So it says Juno is opening her first savings account and is depositing $100. The bank offers 3% annual interest to be calculated at the end of each year. Write a of t function to the amount after time to model the amount of money in Juno savings account after 2 years. So, am I putting money into a bank account and gaining money? Yes. So, because I'm gaining money, I need to make sure that my base that I am using is bigger than 1. So, when I do it, we're going to be using this formula where we start with our principal. We're going to do 1 plus that rate times time. The reason that we're doing 1 plus is because we're increasing in money. If I was losing money, I would be doing 1 minus to get that number below 1. Okay, so my calculator does not recognize the 3% rate, so I'm going to convert that to decimal. So if you're not good at converting it to decimal, take 3 divided by 100. It should give you 0.03. So the amount of money after that time, so my principal is my starting amount, so $100. I'm going to do 1 plus that percentage times that time. So if you want to add that 1 plus 0.03, you're more than welcome to. So calculate the amount of money after 1 year. So after 1 year, we have that $100, 1 plus 0.03 to get me above that 1 as my base. And then we're going to put it in for our time, which is 1 year. So 100, 1 plus 0.03 for my 1 year. We'll have $103 in 1 year, gaining that 3%. So 3% of 100 is $3. So after that year, if I gain 3% each year, I'll have $103. Okay, how about after 5 years? Go ahead and pause the video. Try to do this one in your calculator. I am going to do A of 5 is equal to 100, 1 plus 0.03 to the 5th. And you should be getting $115.93. Okay, so we're going to identify some domain and ranges. We're going to investigate exponentials, asymptotes, increasing and decreasing. We're not going to focus in on end behavior. And what does the number E represent? Okay, so we just kind of looked at this. A is equal to P times 1 plus R to the T, and how we can change it. So I want you guys to do the getting started. So back at towards the end of your book, there's a matching. I want you guys to match your different graphs together, and then we will be talking about them in class. So go ahead and graph the different ones. What do you notice about the bases, their y-intercepts, and go ahead and match those getting started that are at the back of the lesson. And they should look like these. All right, so you're going to be matching this set. And then you're also going to be matching it with the growth and decay, and then filling out the table to kind of match. Okay, this is a growing equation. This is his table. This is his equation. So you're going to kind of put it all together to understand when I have the base be this number, is that a grow or is it a decay? And what are those table values? The big thing we talk about with exponentials are those y-intercepts. So that is why it's focusing on that 0 spot, to focus in on those y-intercepts. Okay, so you're going to talk about what points do the graphs kind of have in common. You're going to compare the equations. You'll notice the differences in the growth from the, the decays. And then we're going to go ahead and roll into 2.1 after you finish that. Okay, so Sarah and Scott's teacher asked them to each write a rule that determines whether a function represents exponential growth or decay based on its equation. So Sarah says for exponential growth functions, b is a value greater than 1. For exponential decay, b is a fraction or decimal between 0 and 1. Scott says for it to grow, b is greater than 1, but for it to decay, it needs to be less than 1, which would be a negative. So if we go ahead and try this, Sarah says, growth here, let's go ahead and put our growth, our decay, our growth, our decay for each person. So for it to grow on this one, it says the b value needs to be greater than 1. So if I make that b value greater than 1, my graph that is going to grow. So go ahead and type in 2 to the x power. You should see that it grows. The next one says a fraction or decimal between 0 and 1. So if I pick, let's say, 0.3, go ahead and graph 0.3 to the x. It should decay. And step says b is greater than 1, so we can use that same 2 to the x, which we already confirmed. But then it says b is less than 1. So something that is less than 1, let's say negative 2. Okay, so notice I did put it in parentheses. If I have the negative on the outside, it will mean something different. So if I go to my y equals here, I type in negative 2. To the x, and I graph it. And then resume. Okay, you don't really see anything. There are dots there. What this is actually doing is not making an exponential, but because I'm reflecting this negative 2, that means I multiply by negative 2 each time. It's going to flip my dots from negative to positive. That is not going to make an exponential equation. It's going to get bigger and bigger dots, not exponentials. So you can't actually have a negative base. You can have a negative on the outside and have it reflect, but a base, that b, cannot be a negative 2. The a can, the b cannot. Okay, so which b values for the function f of x is equal to b to the x produce neither a growth or a decay? So go ahead and try to think about this one. Okay, those are going to be all of my negatives. You can't have a growth or decay when it's a negative. All right, so it says write an exponential function that satisfies the given characteristics. So I increase, meaning it needs to go up. Reference point is 1, 6. So I'm going to put that reference point on there first. Write 1, 2, 3, 4. Okay, so I need to increase through all of my points. Remember, when I do all of my points, I'm going to have that reference point, and I'm going to keep making sure he's uphill. And the next one I'm decreasing with this reference point. So I'm going to put my reference point first, negative 1, 4. And I'm going to make him decrease. Okay. If I do examples of equations here, so if I'm increasing, an example of an equation that will actually work for this is y is equal to 6 to the x power. If I plug that x value of 1 in here, 6 to the 1 is going to give me 6 out in response. So that's kind of interesting to kind of look at the actual equation it makes. So if I was trying to do this one here, one example that I could do, this one's a little bit trickier, is 1/4 to the negative x. To just to the x, sorry. Okay, because if I plug negative 1 in there, that's going to flip that fraction to make him a positive 4. All right, we're going to go ahead and skip that one for now. And we're not going to do this. We're going to be skipping through a decent amount of this just so I can get through the main points. Okay, so in 2.2, Helen is opening her first savings account, is depositing $500. Suppose she decides on a bank account that offers 6% annual interest to be calculated at the end of each year. So it says, write the equation to model the amounts of money in Helen's savings account after 2 years, then determine the amount for 1 year and 5 years. Okay, so similarly to what we did in our original, we're just doing a normal savings account with a normal annual interest. Okay, so we got this here. So the amount of time after my starting amount was 500. We are increasing in money, so I'm going to do 1 plus that rate, 6% in decimal. Okay, and then you're just going to plug the 1 and the t in for this. So you're going to have your first year and your 5th year. So go ahead and either look at their table values. Okay, so you can plug this in to your y equals and look at the table values, or you can physically plug 1 and 5 in. So if you want to plug that into your y equals and then look at the table, okay, for 1 year, you're going to have $530. Let's make sure you label the dollar sign. And then we have $669.11 for year 5. And this next question says, well, suppose the bank decides to start compounding interest at the end of every 6 months. Okay, if they still want to do a 6% for a year, how much interest would per month, 6-month period be? Well, instead of 6%, we're cutting it in half. So we'd actually be doing 3% if we were trying to calculate it. Okay, because it's now based on a 6-month period instead of a year period. If it's 6% for a year, we just got to cut it in half to get that 6-month ratio there. Okay, we're going to go ahead and skip through this. All right, we're going to move past this. Okay, so these ones, what I want you to talk about here is when we are starting to set things up, when we're doing things outside of a year. So just realize if we are doing monthly, how many months are in a year? There are 12 months. So instead of doing it to the first power, you would do it to the 12th. Okay, daily, there are 365 days in a year. So we would be doing it to 365. If we're talking about a daily thing, we're not actually going to go based on the scenario. All right, I'm going to get to, okay, so same thing. Monthly would be your 12, weekly, there are 52 weeks in a year, 365 days. Quarterly, if you think of how many quarters are in $1.04, annually is a year, so semi-annually would be by 2. So kind of just breaking down those numbers a little bit. You won't ever really get asked hourly, minute, or second. Those are the big ones that you might get asked to do. Okay. So what is E? So when we change it up, we're going to be doing compound continuous, which I'll play a video for you that shows what compound continuous means. It's going to be using this E. So E is this number right here. It is a constant number. So when we do exponentials, a lot of times we see like 2 to the x, 3 to the x, 1/2 to the x. This letter E is just this decimal. It's very similar to pi. It doesn't really end, but it is this 2.7 constant. Okay, so when we do compound continuous, instead of using a pretty like 2 base or 3 base, or when we do 1 plus that rate and use that base, we're actually going to use this constant E. So when we do compound continuous, it is going to be something that is done every month, and it is a continuous 2.7 as its base. So that is the rate that these are going to go up by. So when we see this E, it is a button in our calculator that I will show you where it's at. Okay, it's just that constant 2.7 base. So it'd be like saying 2.71 blah, blah, blah to the x power, but we're going to write it as an E. Okay, so if you want to pause the video and go ahead and read this, you're more than welcome to. It's going to kind of explain a little bit more where that E is coming from. All right, and then here's the definition also of where that E is coming from. So the equation that we're going to be kind of looking at is this PERT. That's going to be my compound continuous. So literally when you see the words compound continuously, and I'm going to play a video for you on kind of what compound continuously means. Okay, so what I'm going to do is get this video up. So 1 second. All right, so this is going to explain what compound interest is. Okay, so this is what we have been doing, our simple interest, our simple annual interest. So that's what it's going to explain. So basically what you're doing is you're taking $10,000, you're investing it into a savings account. Every year you're taking 5% of that $10,000, which is in this case $500. Then at the end of 30 years, or in this case 3 years, you'll take all that interest money. So all those $500 that you've gained each year based on that 10,000, and then you'll end up throwing it back into that account, and that's how much money you will have. So you're taking 5% of 10,000 year 1, 5% of 10,000 year 2, 5% of 10,000 year 3, and then you're going to add up all of those to get your total. That is our simple interest. All right, so this is what we refer to as compound continuous. When we do compound continuous, you invest $10,000, you get that 5%, so $500 back. But then you put that $500 back into your bank account, getting ready for the next year. So then you will have $10,500. Then you will take 5% of the $10,500. So you're building interest on the interest. You're putting that interest money back in, and then that total, you're then going to take 5% of again. Whereas when we were doing simple interest, you kept doing it off the original amount, that $10,000. So you're really not gaining as much money. Whereas when you do compound continuously, you're continuously compounding that money every year and doing the interest on top of it. So you're going to see when you do compound continuous, how much quicker it's going to grow because you're building that interest off the original interest of the year before. All right, so let's go ahead and do some actual compound interest equations here. Okay, so it says, suppose, how will invest here's the equation that we're going to use. We call it the PERT equation, okay? So it's continuously going at that 2.7, which is a lot bigger than 1 plus the rate. Okay, because the 1 plus the rate's generally like 1 plus 0.04, 1 plus 0.05. Okay, this is going at a constant of 2 point something, so a lot bigger, a lot quicker. So the amount of time, my principal that I start with is 500. E is a button in our calculator that we're going to use. That's that 2.71. The rate we still need to convert, so my calculator understands it. Remember, if you don't remember how to do the decimal, just take it and divide it by 100. So I'm going to use 0.06 and T for time. So let's go ahead and do our first year. 0.06 times 1. So when I go to my calculator, I'm going to type in 500. Here's how you're going to find it. You're going to press second, and then this little ln that's down here. That's going to prompt me for my exponent, where I'm going to type in my 0.06 times 1. Okay? If you are someone that does not get prompted for the exponent, you have got to use parentheses. So when you type it in, if you get something that looks like this, you need to make sure you type this in parentheses to say they're together. Okay, so the amount of money after 1 year, I have $530.92. Okay, we're going to do the same thing, but with year 5. So I'm going to cheat the system here. I'm going to go up and steal that. And then I'm going to put my 5 in there. $674.93. So after year 5, I have $674.93. $1.93. All right, so that's how we deal with money. I'm gonna show you guys how it looks in population, and then also kind of what it looks like in a graph. So if you actually wanted to graph it, you could look at these different ones, and then if you want to graph e to the x, you can kind of see what that e graph is gonna look like. So I'm gonna press my second, my ln, I'm gonna throw that x in there. Okay, it's gonna just look exactly like a normal exponential function because it really is 2.71 blah 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 to the x power. Okay, so it is an increasing function because it is 2, which is bigger than 1. And then we're going to kind of roll through this and get to this. So in the previous activity, you explored the continuous growth of a principal amount using the value e. We can also use that with population. Okay, so in this, we're going to use this thing that we call the NERT. N naught 0 is the same as the p for principal. Okay, so this is going to be my starting population here. All right, my R is going to be my rate that we're going up by. My T is my time. My N naught is my amount of people after time. Okay, so why is E used as the base? So the constant E is used as the base because the population is continuously growing. The population doesn't increase at set intervals, such as every minute or once a week. It changes continuously. So that is why we are using the E. So how could this formula be used to represent a decline in population? Okay, so I can change this rate of growth to be a negative value to represent a decline in population. So like if I am increasing by 3%, I could change that to a negative 3% and decrease by that percentage. So I could change that rate percent. Okay, I cannot change the base. I don't want to make that E negative. I want to make his rate. So that percentage that I'm growing by or declining by. Okay, so let's go back and grab that equation here. Okay, so it says write the function with this model here. So I'm going to say n of t is equal to my starting population, my E. I have my rate, which is going to be in decimal 0.029 times its time. So then we're going to put some actual time in. So I start at 2000, but I go to 2020. So what is that? How many years is that? If I take 2020 and take off that 2000, I'm going to be plugging in 20 for my years. So A of 20. So go ahead and type it in your calculator. Just a reminder, if you have one of those older 83s or older 84s, when you do this, just make sure all of that is in parentheses. Okay, so now I'm going to type it in. 19360. Make sure I did that right. 19360 e to the 0.029 times 20. So I will have 34,577 people. Notice I did not round up. Yes, it is 0.7. You can't bring a person in. All right. You can't have 0.7 of a person. So I'm just keeping it at that 34,577 people. Okay, so I need to go backwards to 1980. How do I go backwards? I started at 2000. I now need to go backwards 20 years. So I'm going to type in negative 20 and see if I declined back to 1980, how many people could have potentially been there? So I'm going to go up, steal this equation here. I'm going to change this to a negative 20. So around 10,839 people. Notice I'm labeling the people, so I actually know what I'm talking about here. Okay, so there'll be about 10,000 people in 1980. All right, my next one here, use technology to estimate when there are 40,000 people. All right, so first off, let's actually look at this equation here. What do the variables actually mean? T stands for time. AUT stands for the amount of people after time. So I'm actually going to be plugging that 40,000 in here. But the problem is, I don't know how to solve this. I can divide by that 19,360, but how do I get rid of an E? I can't divide by E, okay, because he has his exponent. When you divide by something, it doesn't just make that exponent become a real number there. Okay, so what I'm actually going to do is I'm going to use my graphing calculator, and I want to see when they equal each other. Well, what does it mean when I say I want to know when they equal each other? Well, I want to know when they intersect. So we're going to type this one into y1 and this one into y2, and we're going to see when they actually intersect each other. We're probably going to have to change our window because that's a pretty big number there. So 40,000, or you could look at your table to see when you hit 40,000. 40,000 is pretty exact, so you might actually be able to see it. 1936. 0.029 to the x. Okay, I'm going to change my window. I already know it has to go up 40,000. So my y max, I know I'm already going to make, I'm going to say 41,000 and see if I can see it. Nope, I got to change how far I go to the right. So I'm going to change my x max. We're going to put 50. All right, second trace. Intersect. I'm going to get as close as I can. I'm going to press enter 3 times. This is going to get me past the first curve, the second curve, and then guessing to where it's at. So in 25 years, we will have that 40,000 people.